Neutrino oscillation is a quantum mechanical phenomenon in which a neutrino created with a specific lepton family number can later be measured to have a different lepton family number. The probability of measuring a particular flavor for a neutrino varies between three known states, as it propagates through space. Neutrino oscillation is of great theoretical and experimental interest, as the precise properties of the process can shed light on several properties of the neutrino. In particular, it implies that the neutrino has a non-zero mass, which requires a modification to the standard model of particle physics. The experimental discovery of neutrino oscillation, and thus neutrino mass, by the Super-Kamiokande Observatory and the Sudbury Neutrino Observatories was recognized with the 2015 Nobel Prize for Physics. The idea of neutrino oscillation was first put forward in 1957 by Bruno Pontecorvo, who proposed that neutrino-antineutrino transitions may occur in analogy with neutral kaon mixing. Although such matter-antimatter oscillation had not been observed, this idea formed the conceptual foundation for the quantitative theory of neutrino flavor oscillation, which was first developed by Maki, Nakagawa, and Sakata in 1962 and further elaborated by Pontecorvo in 1967. The concept of neutrino mixing is a natural outcome of gauge theories with massive neutrinos, and its structure can be characterized in general. In its simplest form, it is expressed as a unitary transformation relating the flavor and mass eigenbasis. U alpha I represents the Pontecorvo-Maki-Nakagawa-Sakata matrix, also called the PMNS matrix, or sometimes simply the MNS matrix. It is the analog of the CKM matrix describing the analogous mixing of quarks. If this matrix were the identity matrix, then the flavor eigenstates would be the same as the mass eigenstates. However, experiments show that it is not. The phase factors alpha 1 and alpha 2 are physically meaningful only if neutrinos are Majorana particles, i.e. if the neutrino is identical to its antineutrino and do not enter into oscillation phenomena regardless. If Neutrinoless double beta decay occurs, these factors influence its rate. The phase factor delta is non-zero only if neutrino oscillation violates CP symmetry. If experiments show this 3x3 matrix to be not unitary, a sterile neutrino or some other new physics are required. Solar neutrino experiments combined with CAM land have measured the so-called solar parameters delta M solar squared and sin squared theta solar. Atmospheric neutrino experiments such as Super-Kamiokande together with the K2K and MINO's long baseline accelerator neutrino experiment have determined the so-called atmospheric parameters delta M ATM squared and sin squared theta ATM. The last mixing angle, theta 13, has been measured by the experiments de Bay, Double Shows and Reno. From atmospheric and solar neutrino oscillation experiments, it is known that two mixing angles of the MNS matrix are large and the third is smaller. This is in sharp contrast to the CKM matrix in which all three angles are small and hierarchically decreasing. The CP-violating phase of the MNS matrix is as of April 2020 to lie somewhere between -2 and 165 degrees, from the T2K experiment. If the neutrino mass proves to be of Majorana type, making the neutrino its own antiparticle, it is then possible that the MNS matrix has more than one phase.